In the vast expanse of human discovery, few moments have transformed our understanding of the cosmos as profoundly as the birth of radio astronomy. Before 1932, our window to the universe was limited to what our eyes could see: the twinkling stars, distant galaxies, and the ethereal glow of nebulae. But the universe had more stories to tell, stories that were hidden in wavelengths invisible to the human eye. In 1932, a pivotal moment occurred that would forever change our perception of the cosmos. A young engineer named Karl Jansky, while investigating static interference in transatlantic telephone communications at Bell Telephone Laboratories, detected a mysterious signal coming from the sky. What initially appeared to be mere telecommunications interference would prove to be one of the most groundbreaking discoveries in astronomical history. This is the extraordinary story of how humanity learned to listen to the universe. This revolutionary discovery opened up an entirely new spectrum of cosmic exploration. For the first time, astronomers could detect and study celestial objects and phenomena that were completely invisible to optical telescopes. The radio waves traveling through space began revealing secrets about distant galaxies, explosive stellar events, and the very fabric of the cosmos itself. The impact of radio astronomy on our understanding of the universe cannot be overstated. It revealed previously unknown objects like quasars and pulsars, provided evidence for Einstein's theories, and even gave us a glimpse of the afterglow of the Big Bang through the cosmic microwave background radiation. What began as an accidental discovery transformed into a fundamental pillar of modern astronomy, allowing us to piece together the cosmic puzzle in ways that were unimaginable just a century ago. Through radio astronomy, we learned that the universe is far more dynamic and energetic than we ever imagined. We discovered that space isn't silent at all. It's filled with a symphony of radio emissions, telling stories of violent cosmic collisions, the birth and death of stars, and the mysterious dance of invisible matter. This new way of observing the cosmos has not only expanded our understanding of the universe, but has also led to practical applications that we use in our daily lives, from Wi-Fi technology to GPS systems. Before we delve deeper into this fascinating journey through the history of radio astronomy, don't forget to like and subscribe to Exploring the Universe channel to ensure you never miss any content about the fascinating world of astronomy. Join us as we explore how a simple investigation of radio interference transformed into one of the greatest astronomical revolutions in human history. This incredible story reminds us that sometimes the most revolutionary discoveries come from unexpected places, and that the universe is always ready to surprise us, if we're just willing to listen in new ways. Together, we'll explore how this accidental discovery grew into a scientific field that continues to push the boundaries of human knowledge and reshape our understanding of the cosmic ocean we call home. In the early 1930s, at the height of the Great Depression, a young radio engineer named Karl Jansky was working on what seemed to be a routine problem at Bell Telephone Laboratories in Holmdel, New Jersey. His assignment was straightforward yet crucial: identify the sources of static interference that were plaguing the company's shortwave transatlantic radio communications. To tackle this challenge, Jansky designed and built a peculiar-looking antenna that would soon make history. Standing 20 feet tall and mounted on a wooden turntable from a Model T Ford, this contraption could rotate in a complete circle every 20 minutes. Local residents dubbed it Jansky's merry-go-round, but its official name was the Grote Array. The antenna was designed to receive radio waves at a frequency of 20.5 MHz, and its rotating capability allowed Jansky to determine the direction of any interference sources. For months, Jansky meticulously recorded and analyzed the static. He quickly identified two obvious sources: nearby and distant thunderstorms. However, there was a third type of static, a faint but persistent hiss that puzzled him. This mysterious signal seemed to peak every 23 hours and 56 minutes, exactly one sidereal day, the time it takes for the Earth to complete one rotation relative to the stars. This timing was the key that unlocked a cosmic mystery. Jansky noticed that the signal was strongest when his antenna pointed toward the constellation Sagittarius, in the direction of the center of our Milky Way galaxy. After months of careful observation and analysis, he reached an extraordinary conclusion. The static was coming from space itself. Specifically, he had detected radio waves emanating from the heart of our galaxy. In 1933, Jansky's discovery was published in various publications, including the New York Times, and he presented his findings to the International Scientific Radio Union. What had begun as a telecommunications troubleshooting project had unexpectedly birthed an entirely new field of astronomy. Jansky had become the first person to detect radio waves from an astronomical source, proving that celestial objects emit not just visible light, but radio waves as well. The significance of this accidental discovery cannot be overstated. Just as Galileo's telescope had revealed previously invisible moons and mountains, Jansky's antenna had opened up an entirely new window through which to observe the universe. His work demonstrated that we could study cosmic phenomena through radio waves, leading to the development of radio astronomy. Perhaps most remarkably, Jansky made this groundbreaking discovery using an antenna that cost less than $2,000 to build. The equipment was primitive by today's standards. The entire rotating mechanism was driven by a small motor and bicycle chain, and the data was recorded by hand. Yet this humble apparatus revealed an entirely new aspect of our universe, proving once again that sometimes the most significant scientific discoveries come from the most unexpected places. Unfortunately, Bell Labs, focused on solving their immediate communication problems, didn't pursue this astronomical discovery further. Jansky was assigned to other projects, and it would be several years before another pioneer, Grote Reber, would build upon his work. Nevertheless, Jansky's accidental discovery had set in motion a chain of events that would revolutionize our understanding of the cosmos. Today, the unit used to measure the strength of radio sources in astronomy is named the Jansky in his honor, and his original antenna design has been replicated and stands as a monument at the National Radio Astronomy Observatory in Green Bank, West Virginia. This remarkable story of serendipity, careful observation, and groundbreaking discovery remains one of the most important chapters in the history of astronomy, demonstrating how solving a simple terrestrial problem led to one of humanity's greatest tools for understanding the universe. While the astronomical community largely ignored Jansky's groundbreaking discovery, one amateur astronomer in Wheaton, Illinois, recognized its profound implications. Grote Reber, a 26-year-old radio engineer, became captivated by Jansky's work and decided to pursue what others had overlooked. In 1937, he embarked on an extraordinary endeavor, building the world's first dedicated radio telescope in his own backyard. Using his skills as a radio engineer and investing nearly $2,000 of his own money during the Great Depression, Reber designed and constructed something unprecedented. His creation was a massive parabolic reflector, 31, 4 feet in diameter and 20 feet high, built from wood and sheet metal. The neighbors must have thought him eccentric, as this strange dish-shaped structure rose above their suburban landscape. While they tended their gardens, Reber was literally reaching for the stars. The construction process was a testament to his ingenuity and determination. He worked mostly alone, fabricating the wooden framework and carefully shaping the metal surface to form a precise parabola. The telescope was mounted on a tilting mechanism that allowed it to scan different portions of the sky, though it couldn't rotate fully like Jansky's antenna. Working during the day as an engineer and spending his nights observing the cosmos, Reber pursued his passion in almost complete scientific isolation. For nearly 2 years, Reber's attempts to detect cosmic radio waves met with frustration. His initial receivers, operating at the same frequency as Jansky's, failed to pick up significant signals. Rather than give up, he persisted, experimenting with different frequencies until he finally achieved success using a lower frequency of 160 MHz. This breakthrough led to his first detection of radio emissions from the Milky Way in 1938. What followed was a remarkable achievement. Over several years of solitary nighttime observations, Reber created the first radio map of our galaxy. Published in 1944, this unprecedented survey showed the distribution of radio emissions across the sky, revealing a new view of our cosmic home that was invisible to optical telescopes. His maps demonstrated concentrations of radio sources in the galactic plane and particularly intense emissions from the constellation Cygnus, findings that would later prove crucial to understanding our galaxy's structure. The loneliness of Reber's pioneering work cannot be overstated. For nearly a decade, he was literally the world's only active radio astronomer. He submitted his findings to various scientific journals, but many astronomers were skeptical or simply uninterested. The astronomical community, deeply rooted in traditional optical observations, was slow to recognize the significance of radio astronomy. Reber often remarked that he felt like a voice in the wilderness, pursuing a field of study that most of his contemporaries either didn't understand or didn't believe in. Yet Reber's persistence would ultimately be vindicated. After World War II, when radar technology experts turned their attention to astronomy, they found that this solitary pioneer had already laid much of the groundwork for their field. His publications became foundational documents for the emerging discipline of radio astronomy, and his homemade telescope design influenced the construction of many professional instruments that followed. Perhaps most remarkably, Reber never sought to profit from or patent his innovations. He freely shared his designs and findings, motivated purely by scientific curiosity and the desire to understand the universe better. When radio astronomy finally gained mainstream acceptance in the 1950s and 60s, Reber was rightfully recognized as its founding father, though he maintained his independent spirit, often pursuing unconventional research interests that put him at odds with the scientific establishment. Today, Reber's original telescope no longer stands in that Wheaton backyard, but it is preserved at the National Radio Astronomy Observatory in Green Bank, West Virginia, alongside a replica of Jansky's antenna. These monuments serve as testimonies to how individual curiosity, determination, and willingness to explore the unknown can open entirely new frontiers in our understanding of the cosmos. Reber's story reminds us that sometimes the most significant scientific advances come not from large institutions, but from dedicated individuals working in solitude, driven by nothing more than an insatiable curiosity about the universe. The post-World War II era marked an explosive transformation in radio astronomy, turning what was once a solitary pursuit into a major scientific endeavor. The war, despite its devastating toll, had inadvertently prepared the ground for this revolution through the rapid advancement of radar technology. During World War II, nations had invested heavily in radar development for military purposes, training thousands of engineers and technicians in radio technology. When peace finally came, this expertise found a new purpose. Many radar specialists, now skilled in detecting and analyzing radio signals, turned their attention to the mysteries of the cosmos. The sophisticated radar equipment, once used to track enemy aircraft, was repurposed to study celestial objects. In Cambridge, England, a former radar researcher named Martin Ryle would revolutionize the field by developing radio interferometry. This innovative technique combined signals from multiple antennas to achieve much higher resolution than any single antenna could provide. Ryle's work was groundbreaking. By connecting two or more radio telescopes, He could create a virtual telescope with the equivalent size of the distance between them. This breakthrough allowed astronomers to pinpoint radio sources with unprecedented precision and ultimately led to Ryle being awarded the Nobel Prize in Physics in 1974. The birth of modern radio observatories transformed isolated experiments into coordinated scientific efforts. Around the globe, former radar stations were converted into astronomical facilities, and new purpose-built observatories began to emerge. In Australia, the CSIRO Radio Physics Laboratory established multiple observing stations. In the Netherlands, the Dwingeloo Radio Observatory was constructed. The United States saw the establishment of the National Radio Astronomy Observatory in Greenbank, West Virginia. Perhaps no facility better exemplifies this post-war transformation than the Jodrell Bank Observatory in Cheshire, England. Under the leadership of Bernard Lovell, another former radar researcher, the observatory constructed what was then the world's largest steerable radio telescope. The massive 250-foot, 76-meter dish of the Lovell telescope, completed in 1957, became an icon of the new era in astronomy. Initially viewed with skepticism due to its enormous cost and engineering challenges, the telescope proved its worth almost immediately by tracking the Soviet Union's Sputnik 1 satellite, and later played crucial roles in both astronomical research and the space race. The rapid growth of radio astronomy during this period led to a cascade of discoveries. Astronomers began detecting previously unknown objects and phenomena, quasars, pulsars, and radio galaxies. The field that had begun with Jansky's accidental discovery and continued through Reber's solitary efforts had blossomed into a sophisticated scientific discipline with dedicated institutions, peer-reviewed journals, and international collaborations. This post-war explosion in radio astronomy also demonstrates how technology developed for warfare can be transformed into tools for understanding our universe. The same principles that had been used to detect enemy aircraft were now revealing the secrets of distant galaxies. The precision timing needed for radar systems proved essential for studying pulsars. The signal processing techniques developed for military communications became fundamental to analyzing cosmic radio emissions. The era marked a fundamental shift in how astronomy was conducted. No longer was it solely the domain of optical telescopes and solitary observers. Radio astronomy had introduced new ways of observing, new types of instruments, and new kinds of collaboration. It showed that the universe had many stories to tell, if only we learned to listen in the right ways. And speaking of revolutionary discoveries that people initially doubted, we'd love to hear from you. What would you do if you discovered something revolutionary and nobody believed you? Share your thoughts in the comments below. Would you persist like Grote Reber, building evidence in your backyard? Or would you seek different ways to convince the scientific community? Your perspective might inspire others facing similar challenges in their pursuits. The post-war explosion in radio astronomy serves as a powerful reminder that sometimes the greatest scientific advances come from repurposing existing technology in new and unexpected ways. It shows how the collective expertise of many individuals, when turned from military purposes to peaceful scientific exploration, can open new windows onto the universe and fundamentally change our understanding of the cosmos. The 1960s marked a golden age for radio astronomy, producing discoveries that would fundamentally change our understanding of the universe. Let's explore these remarkable breakthroughs that reshaped modern cosmology. In 1963, astronomer Martin Schmidt made a discovery that would stun the scientific community. While studying what appeared to be a peculiar star called 3C273, Schmidt realized he was looking at something far more exotic. The object's spectral lines were shifted to such an extreme degree that it had to be incredibly distant, billions of light years away. Yet despite this vast distance, it appeared brighter than many nearby galaxies. Schmidt had discovered the first quasar, quasi-stellar object, revealing the existence of the most luminous objects in the known universe. These cosmic beacons turned out to be powered by supermassive black holes at the centers of distant galaxies, devouring surrounding matter with such ferocity that they outshine their entire host galaxies. Just a year later, in 1964, Arno Penzias and Robert Wilson at Bell Laboratories encountered what they initially thought was an annoying problem. Their radio antenna was picking up mysterious background noise that wouldn't go away. After ruling out every possible source of interference, including famously cleaning pigeon droppings from their antenna, they realized they had stumbled upon something extraordinary: the cosmic microwave background radiation. This faint radio glow, uniform across the entire sky, was nothing less than the afterglow of the Big Bang itself, the oldest light in the universe. This accidental discovery provided the strongest evidence yet for the Big Bang theory, and earned Penzias and Wilson the 1978 Nobel Prize in Physics. Perhaps one of the most remarkable discoveries came in 1967 when graduate student Jocelyn Bell Burnell, working with her thesis advisor Anthony Hewish at Cambridge University, detected an unusual signal, a steady pulse of radio waves occurring every 1.3 seconds with clock-like precision. Initially dubbed Little Green Man 1 due to its artificial-seeming regularity, this signal turned out to be something equally extraordinary: the first pulsar ever discovered. Pulsars are rapidly rotating neutron stars, the incredibly dense remnants of massive stars that have exploded as supernovae. These cosmic lighthouses beam radio waves into space like celestial beacons, providing astronomers with natural laboratories for testing theories of extreme physics. However, these groundbreaking discoveries also sparked controversy in the scientific community, particularly regarding recognition and credit. The most notable controversy surrounds the 1974 Nobel Prize in Physics, awarded to Hewish and Ryle for their work in radio astronomy, including the discovery of pulsars. Many in the scientific community felt that Bell Burnell, who had made the actual discovery of pulsars, should have shared in the prize. Her exclusion became a prominent example of the Matilda effect, the systematic under-recognition of women's contributions to science. The discoveries themselves also challenged existing theories and sparked heated debates. Quasars, for instance, were initially met with skepticism because their enormous energy output seemed to defy the laws of physics. How could objects be so bright and so distant? The explanation, supermassive black holes, was itself a controversial concept at the time. The cosmic microwave background discovery initially faced similar skepticism, though it quickly gained acceptance as supporting evidence accumulated. These discoveries revolutionized our understanding of the universe in fundamental ways. Quasars showed us that the early universe was far more active and energetic than previously thought. Pulsars provided natural laboratories for studying matter under extreme conditions and gave us precise tools for testing Einstein's theory of relativity. The cosmic microwave background offered a window into the earliest moments of our universe's history and continues to be a crucial tool in modern cosmology. The legacy of these discoveries extends far beyond their initial impact. Pulsars are now used as cosmic clocks for testing gravitational theories and could potentially serve as natural navigation beacons for future space missions. The cosmic microwave background has become our primary window into the early universe, helping us understand everything from the distribution of matter to the age of the universe itself. Quasars serve as cosmic beacons, allowing us to probe the space between galaxies and study the evolution of the universe on the largest scales. These breakthroughs of the 1960s remind us that revolutionary discoveries often come unexpectedly, and that the process of scientific recognition doesn't always match the reality of scientific discovery. They stand as testaments to the power of careful observation, the importance of being open to unexpected results, and the need to ensure proper recognition for all contributors to scientific advancement. The technological evolution of radio astronomy represents one of the most impressive achievements in modern science. Let's explore how these remarkable instruments have transformed our ability to study the cosmos. The Very Large Array in New Mexico stands as one of the most iconic radio observatories ever built. Completed in 1980, it consists of 27 identical radio antennas, each measuring 82 feet in diameter, arranged in a Y-shaped configuration. What makes the VLA revolutionary is its ability to combine these 27 dishes into a single virtual telescope. The antennas can be moved along railroad tracks, spreading out over distances up to 22 miles, allowing astronomers to achieve different levels of resolution. This flexibility makes the VLA one of the most versatile instruments in radio astronomy, capable of studying everything from nearby planets to distant galaxies. The VLA has been crucial in studying phenomena like black holes, radio galaxies, and the aftermath of supernovae, providing some of the most detailed radio images of the cosmos ever created. The Arecibo Observatory in Puerto Rico was, for many decades, a testament to human ingenuity and ambition. Built into a natural sinkhole in 1963, its massive 1,000-foot dish was the world's largest single-aperture telescope until its unfortunate collapse in 2020. Unlike conventional telescopes, Arecibo's dish was fixed, with its receivers suspended on cables 450 feet above. Despite its static nature, Arecibo made groundbreaking discoveries, including the first binary pulsar, which provided crucial evidence for gravitational waves, detailed radar maps of planets and asteroids, and the first repeating fast radio burst. The observatory also played a significant role in the search for extraterrestrial intelligence, sending the famous Arecibo message into space in 1974. High in the Atacama Desert of Chile, at an elevation of 16,400 feet, sits one of humanity's most ambitious astronomical projects, the Atacama Large Millimeter Submillimeter Array. Completed in 2013, ALMA consists of 66 high-precision antennas working together as a single telescope. What makes ALMA unique is its ability to observe the universe in millimeter and submillimeter wavelengths, allowing it to peer through cosmic dust clouds that block visible light. This capability has revolutionized our understanding of planet formation, revealed the chemical composition of distant galaxies, and provided unprecedented views of star-forming regions. The extreme altitude and dry conditions of the Atacama Desert make it an ideal location for these observations, though they also present significant challenges for the scientists and engineers who maintain the facility. Looking to the future, the Square-Kilometer Array represents the next quantum leap in radio astronomy. Currently under construction in South Africa and Australia, the SKA will be the world's largest radio telescope when completed. The project's name comes from its total collecting area of 1 square kilometer, achieved through hundreds of dishes in South Africa and thousands of smaller antennas in Australia. The SKA's unprecedented sensitivity and speed will revolutionize our understanding of the universe. It will be able to detect extremely faint radio signals from the early universe, potentially revealing the formation of the first stars and galaxies. The project will generate enormous amounts of data, equivalent to the entire current global internet traffic, requiring new developments in computing and data processing. Each of these facilities represents a different approach to the challenges of radio astronomy. The VLA demonstrates the power of interferometry and flexibility. Arecibo showed how natural geography could be used to create unprecedented collecting area. ALMA proves the value of specialized instruments in extreme locations. The SKA represents the future of big data in astronomy. The evolution of these instruments has been driven by advancing technology and our growing understanding of the universe. Modern radio telescopes utilize sophisticated electronics, superconducting detectors, and powerful computers to process the incoming signals. The development of reliable cryogenic systems has allowed receivers to be cooled to near absolute zero, dramatically reducing electronic noise and improving sensitivity. This technological evolution continues today. Innovations in digital signal processing, artificial intelligence, and machine learning are being incorporated into radio astronomy, allowing astronomers to handle ever larger datasets and detect increasingly subtle phenomena. The future promises even more advanced instruments, with proposals for radio telescopes in space and on the far side of the moon, where they would be shielded from Earth's radio interference. The story of radio telescope evolution is not just about bigger dishes or more sensitive receivers. It's about human ingenuity, finding new ways to explore the cosmos. Each new generation of instruments has opened new windows onto the universe, revealing phenomena that previous generations of astronomers could hardly have imagined. As we look to the future with projects like the SKA, we can only wonder what new cosmic mysteries these extraordinary instruments will help us uncover. The title of largest single-dish radio telescope in the world now belongs to China's 500-meter aperture spherical radio telescope, which began operations in 2016. This massive instrument, nicknamed Tianyan, or Heaven's Eye, is built into a natural depression in Guizhou province. Its reflecting surface spans 500 meters in diameter, large enough to cover 30 football fields. Unlike its predecessor, Arecibo, FAST features an active surface that can deform to create parabolas in different directions, allowing it to observe a larger portion of the sky. The scale of this project is mind-boggling. The telescope's collecting area is equivalent to 450 Olympic-sized swimming pools, and its sensitivity is remarkable enough to detect a cell phone call made from the surface of Mars. The history of radio astronomy is rich with accidental discoveries that transformed our understanding of the cosmos. Beyond Jansky's initial detection of cosmic radio waves, several other serendipitous findings stand out. The cosmic microwave background radiation was famously discovered when Penzias and Wilson were trying to eliminate what they thought was noise in their antenna. The first pulsar was detected when Jocelyn Bell Burnell noticed an unusual bit of scruff in her data that turned out to be a rapidly rotating neutron star. Even the technology for Wi-Fi emerged accidentally from radio astronomy research when scientists at Australia's CSIRO were working on a way to detect exploding mini black holes. Among the most intriguing aspects of radio astronomy are the unexplained signals that continue to puzzle scientists. The WOW signal, detected by Ohio State University's Big Ear radio telescope in 1977, remains one of the most famous. This powerful narrowband radio signal lasted for 72 seconds and bore expected hallmarks of potential extraterrestrial intelligence. But it has never been detected again, despite numerous searches. Its source remains a mystery to this day. The signal was so remarkable that astronomer Jerry Eman wrote "Wow" on the computer printout, giving the signal its famous name. Bust radio bursts represent one of the most exciting and mysterious phenomena in modern astronomy. These incredibly powerful flashes of radio waves last for just milliseconds, but can release as much energy as the sun produces in decades. First discovered in 2007, FRBs were initially thought to be one-time events. However, the discovery of repeating FRBs in 2016 changed our understanding of these enigmatic signals. Scientists have now detected hundreds of FRBs from different parts of the sky, but their exact cause remains debated. Theories range from magnetar flares to alien megastructures, though most astronomers favor natural explanations involving highly magnetized neutron stars. Other mysterious radio phenomena include the Great Wall of radio emission discovered in 2013, spanning nearly 1 billion light-years, and the radio circles discovered in 2020. Giant rings of radio emission that don't seem to correspond to any known type of object or phenomenon. These discoveries remind us that even after nearly a century of radio astronomy, the universe still has plenty of surprises in store. The field has also revealed unexpected patterns in seemingly random signals. For instance, the discovery of periodic patterns in what were thought to be random pulsar emissions has led to new insights into stellar physics. Similarly, the detection of complex organic molecules in space through their radio signatures has revolutionized our understanding of astrochemistry and the potential for life in the universe. Some of the most intriguing mysteries come from our own galaxy. The center of the Milky Way emits unusual radio patterns that don't fit conventional models of galactic structure. Strange radio filaments, some stretching for hundreds of light years, cross the galactic center region, and their origin remains debated. These structures, invisible to optical telescopes, remind us that there's still much to learn about our cosmic home. Modern radio telescopes continue to push the boundaries of what we can detect and observe. New instruments like FAST and the upcoming SKA promise to reveal even more mysteries and perhaps solve some long-standing ones. They might help us understand the nature of FRBs, detect new types of astronomical phenomena, or even pick up signals from other civilizations. The ongoing discovery of unexplained signals and phenomena highlights an important aspect of science. Not every mystery needs to be solved immediately. Sometimes, the very existence of these puzzles drives technology forward and inspires new generations of scientists to look at the cosmos in different ways. As our instruments become more sensitive and our analysis techniques more sophisticated, we continue to find that the universe is even stranger and more fascinating than we imagined. The first radar contact with Venus in 1961 marked a pivotal moment in planetary exploration. Using the newly operational 26-meter radio telescope at Goldstone Observatory, scientists successfully bounced radar signals off Venus's surface, receiving the echoes after traveling over 70 million kilometers through space. This achievement not only proved the feasibility of planetary radar astronomy, but also provided the first precise measurement of the Earth-Venus distance. The experiment revealed surprising details about Venus's rotation, discovering that the planet rotates backwards compared to most other planets and much more slowly than previously thought. This breakthrough opened the door for radar mapping of other planets and asteroids, fundamentally changing our approach to solar system exploration. The discovery of the first binary pulsar in 1974 by Russell Hulse and Joseph Taylor at Arecibo Observatory stands as one of radio astronomy's greatest achievements. This system, designated PSR B1913+16, consists of two neutron stars orbiting each other, with one visible as a pulsar. The precision timing of the pulsar signals allowed astronomers to observe the effects of gravitational waves for the first time, as the orbital period of the system gradually decreased exactly as predicted by Einstein's theory of general relativity. This indirect detection of gravitational waves earned Hulse and Taylor the 1993 Nobel Prize in Physics, and provided the first empirical evidence for gravitational waves, decades before their direct detection by LIGO in 2015. The mapping of the galactic center revolutionized our understanding of the Milky Way. Beginning in the 1970s and continuing through today, radio observations revealed the complex structure of our galaxy's core, hidden behind thick clouds of dust that block visible light. The discovery of Sagittarius A, the compact radio source at the very center of our galaxy, provided the first evidence for the supermassive black hole that lurks there. Radio observations tracked stars orbiting this invisible object, definitively proving its existence and measuring its mass at about 4 million times that of our Sun. This long-term project demonstrated the power of radio astronomy, to pierce through cosmic obstacles that limit optical astronomy. Perhaps one of the most surprising developments in radio astronomy was the detection of complex organic molecules in space. In 1968, the discovery of ammonia in interstellar space was followed by increasingly complex molecules. The detection of formaldehyde in 1969 marked the first discovery of an organic molecule in interstellar space. Radio astronomers have since identified hundreds of molecules, including alcohols, sugars, and even amino acids, the building blocks of proteins. The discovery of ethyl alcohol in giant clouds near the center of our galaxy showed that complex organic chemistry isn't unique to Earth. These findings revolutionized our understanding of astrochemistry and raised intriguing questions about the origins of life's chemical precursors. Particularly noteworthy was the 1994 detection of glycolaldehyde, the simplest sugar molecule in the interstellar medium. This finding suggested that the basic ingredients for life might be more common in the universe than previously thought. Radio observations continue to reveal increasingly complex organic molecules in space, supporting the idea that the chemical foundations for life might have cosmic origins. These historic events share a common thread. They each challenged existing paradigms and opened new avenues for research. The radar contact with Venus inaugurated a new era of planetary exploration. The binary pulsar provided the first laboratory for studying extreme gravity. The mapping of the galactic center revealed the dynamic heart of our galaxy. The detection of organic molecules in space suggested possible cosmic origins for life's building blocks. Each discovery built upon previous work while pointing the way toward future investigations. The success with Venus radar led to detailed mapping of Mercury, Mars, and various asteroids. The binary pulsar discovery spurred the search for other exotic stellar systems. The galactic center studies continue to reveal new details about black hole physics. The detection of organic molecules drives ongoing searches for increasingly complex compounds in space. These landmarks also demonstrate radio astronomy's unique ability to reveal aspects of the universe invisible to other forms of observation. From penetrating the clouds around the galactic center to detecting complex molecules in space, radio astronomy has repeatedly proven its value in uncovering cosmic secrets that would otherwise remain hidden. As technology continues to advance, we can only imagine what other historic discoveries await in the radio sky. The contributions of radio astronomy have transcended the realm of space exploration, deeply embedding themselves into everyday technologies that shape modern life. One of the most notable outcomes is the development of Wi-Fi technology. In the 1990s, researchers at CSIRO in Australia, while working on methods to correct distortions in radio signals caused by environmental interference, inadvertently pioneered the technology behind wireless networking. By adapting their techniques for local data transmission, they laid the groundwork for the high-speed wireless internet we rely on today. This transformation showcases how innovations initially aimed at unraveling the universe's mysteries can redefine connectivity on Earth, fueling everything from education to global commerce. Advancements in telecommunications owe a significant debt to radio astronomy. The principles and technologies honed in the study of cosmic radio waves have directly influenced the development of satellite communication systems. Techniques for capturing and processing faint signals from deep space have been adapted to improve clarity, speed, and reliability in transmitting data across the globe. Furthermore, the construction of massive radio telescopes inspired the engineering of parabolic antennas, a cornerstone in modern satellite technology. This interplay between astronomy and telecommunications exemplifies how exploring the stars has enabled more efficient global communication, bringing the world closer together. The technology behind GPS, or Global Positioning System, is another revolutionary application rooted in radio astronomy. GPS relies on precise timing and the accurate interpretation of radio signals from a network of satellites. Early experiments in radio wave propagation and signal timing, fundamental to radio astronomy, informed the development of systems capable of determining positions with unparalleled accuracy. These advancements have transformed navigation, logistics, agriculture, and emergency response, demonstrating how astronomical research has practical implications for everyday life, enabling people to traverse vast landscapes with the touch of a button. Finally, radio astronomy has played a crucial role in the emerging field of space weather forecasting. By monitoring the sun's radio emissions, scientists can detect solar flares and coronal mass ejections, phenomena capable of disrupting Earth's magnetic field, satellites, and electrical grids. The ability to predict and prepare for such events is vital for safeguarding modern technology-dependent societies. Through continuous observation of space weather patterns, radio astronomers provide critical insights that protect both infrastructure and human safety, ensuring that technological progress is resilient against cosmic challenges. The seamless integration of these innovations into daily life underscores the transformative power of radio astronomy. By listening to the universe, humanity has not only expanded its cosmic horizons, but also harnessed the tools to redefine communication, navigation, and global connectivity. These achievements are a testament to the profound impact of exploring the unseen, where the pursuit of knowledge catalyzes progress across every facet of civilization. The future of radio astronomy is poised to revolutionize our understanding of the cosmos with groundbreaking projects, technological advancements, and a relentless quest to answer one of humanity's most profound questions. Are we alone in the universe? As we look ahead, several ambitious initiatives and cutting-edge innovations promise to push the boundaries of what radio telescopes can achieve, paving the way for discoveries that were once relegated to the realm of science fiction. New projects under development represent a quantum leap in radio astronomy's capabilities. At the forefront is the Square Kilometre Array, a global collaboration that will construct the most powerful radio telescope ever conceived. Spread across South Africa and Australia, the SKA will boast a total collecting area of 1 square kilometre, enabling it to detect faint radio signals from the universe's earliest epochs. This unprecedented sensitivity will allow astronomers to study the formation of the first galaxies, explore dark matter, and trace the cosmic web in unparalleled detail. Similarly, China's FAST telescope, operational since 2016, continues to refine its capabilities and expand its scientific output, leading efforts to uncover new pulsars, fast radio bursts, and potentially extraterrestrial signals. These projects highlight how international cooperation is driving the next era of cosmic exploration. Technological challenges remain a key focus as radio astronomy evolves. One of the most pressing issues is the growing threat of radio frequency interference from Earth-based sources, including satellites, wireless networks, and urban development. This pollution of the radio spectrum threatens to drown out the faint cosmic signals astronomers rely on. To mitigate this, scientists are exploring solutions like building telescopes in remote shielded locations, such as the far side of the Moon, where Earth's interference is virtually non-existent. Another challenge is managing the sheer volume of data generated by next-generation telescopes like the SKA, which will produce exabytes of information annually. Advances in artificial intelligence and machine learning are being integrated into data processing pipelines, allowing astronomers to analyze and interpret these vast data sets efficiently. Developing energy-efficient computing systems to handle such demands is also critical to ensuring the sustainability of these massive projects. The search for extraterrestrial life is one of radio astronomy's most captivating pursuits. With tools like the SKA and other advanced facilities, scientists are intensifying efforts to detect biosignatures and technosignatures from distant worlds. These could include artificial radio signals from advanced civilizations or natural emissions from planets with conditions suitable for life. Projects like the Breakthrough Listen initiative are leveraging state-of-the-art telescopes to scan millions of stars for potential signs of intelligent life, while new methods of observing exoplanets' atmospheres through their radio emissions are being developed. These techniques could help identify habitable environments or even confirm the presence of life beyond Earth, answering a question that has fascinated humanity for centuries. The next generation of radio instruments will redefine our observational capabilities, unlocking new windows into the universe. Among these innovations are space-based radio telescopes, which will overcome the limitations of Earth's atmosphere and RFI, enabling clearer observations of low-frequency radio waves. Concepts like the Lunar Crater Radio Telescope, proposed for the Moon's far side, promise to explore the universe's dark ages, a period shortly after the Big Bang that remains inaccessible to current technology. Additionally, interferometry networks like the Event Horizon Telescope are expanding their arrays to achieve even sharper images of black holes and other extreme phenomena. This era will also witness the integration of multi-messenger astronomy, where radio observations will work alongside gravitational wave detectors, neutrino observatories, and optical telescopes to provide a more comprehensive picture of cosmic events. As humanity ventures further into space, the role of radio astronomy will become even more crucial. From tracking spacecraft across the solar system to understanding the hazards of space weather, these advancements will ensure that exploration is both informed and safe. The technologies developed for radio astronomy will continue to spill over into other fields, driving innovation in telecommunications, navigation, and data science. The future of radio astronomy is not just about observing the cosmos, it is about forging deeper connections between science, technology, and humanity's enduring curiosity about its place in the universe. Through its ever-expanding horizons, radio astronomy will guide us toward discoveries that challenge our understanding and inspire future generations to look to the stars. As we reach the conclusion of this journey through the fascinating world of radio astronomy, it is impossible not to marvel at the profound legacy left by its pioneers. Visionaries like Karl Jansky and Grote Reber, who laid the foundations of this field with their groundbreaking discoveries and unwavering curiosity, transformed our understanding of the universe. Their work opened an entirely new window into the cosmos, allowing us to explore phenomena invisible to optical telescopes and providing a deeper understanding of celestial mechanics, galactic structures, and the very origins of the universe. The efforts of these trailblazers remind us that scientific progress often begins with individuals daring to look at the world, or the universe, in ways no one has before. The importance of radio astronomy to modern science cannot be overstated. It has fundamentally reshaped our perception of the cosmos, revealing quasars, pulsars, and the cosmic microwave background radiation. These discoveries have not only expanded the boundaries of astronomy, but have also validated critical theories, such as Einstein's general relativity, and provided insights into the Big Bang. Beyond its contributions to our cosmic understanding, radio astronomy has fostered technological innovations that permeate daily life, from Wi-Fi to GPS. Its role in advancing space exploration, telecommunications, and data processing demonstrates how this field bridges the gap between the stars and our lives on Earth. In essence, radio astronomy is a testament to humanity's unyielding quest to understand its place in the universe. As we look to the future, the legacy of these early discoveries continues to inspire a new generation of astronomers, engineers, and enthusiasts to push the limits of what is possible. The advancements being made today, from the construction of the square-kilometer array to the exploration of the universe's earliest epochs, are direct extensions of the groundwork laid by those who dared to ask the big questions. Radio astronomy is not merely a field of study, it is a story of human ingenuity, perseverance, and a shared curiosity about the unknown. It connects the past, present, and future in a quest to uncover the mysteries of the cosmos. To continue exploring this incredible journey, be sure to subscribe to the channel Exploring the Universe. Activate the notification bell to stay updated on all our content and never miss a single discovery. If you enjoyed this deep dive into the wonders of radio astronomy, leave a like to show your support and share this video with your friends. Together, we can inspire others to look up at the stars and wonder what lies beyond. Thank you for joining us on this adventure. Let's keep exploring the universe, one discovery at a time.